Okay, uh, let me begin today's session. So this is tutorial session 7 for the course NPTEL course on variation calculus and its applications in control theory and nanomechanics. I am Jia Noether, a PhD scholar at the Indian Institute of Science, Bangalore. Okay, so today I will be covering week 8 of the course and also review the concepts that were discussed in the lectures, and then we'll follow it up with discussing and solving a bunch of problems. So, in the review part, we'll be uh, taking a look at variational symmetry and Noether's theorem, and the second variation. So let's start with the first. Let's review the first topic, which is Noether's theorem, and let's first discuss about review the what the meaning of a conservation law. So mathematically, say we have a functional j of y over integrated over, which is defined as, which is expressed as integrand f of, which is whose arguments are x, y, y prime till nth derivative of y. This integrand is integrated over domain x0 to x1. Now suppose there exists a function phi um, of x, y, y prime till yk, such that the derivative of this function with respect to x is 0 for all extremals y of j. Then this expression, is called the kth order conservation law for the functional j. Now you're very familiar uh, with the conservation laws in mechanics, such as conservation, the most famous and fundamental being conservation of energy, and then follow it up with conservation of momentum and conservation of linear momentum. So now what Noether's theorem does is, Noether's theorem links conservation law with the invariance properties of the functional. And the crux of finding conservation laws always lies with finding the symmetries in the functional. So these symmetries are what we call as the transformations. So what we do is we essentially make transformations to the arguments of the functional, of the integrand of the functions such this, and for the transformations under which the functional is invariant, those transformations are what we call as the variational symmetries. Now let's come to variational symmetries. Let's take the very basic functional, which we have been discussing a lot in this course, which is defined as j of y is fx y prime integrated over x0 to x1. Now the integrand of this functional is variously invariant over x0 and x1 over the domain x0 x1 under transformation. The transformation is capital X is equal to theta, which is a function of x, y, epsilon, and capital Y is equal to psi x, y, epsilon, and epsilon here is a parameter. So transformations of such form are what we call as, it's essentially a one parameter family of transformations, because epsilon is the parameter which we are varying in order to obtain uh, the transformation capital X, capital Y. Now f is variously invariant over x0 x1 under this transformation if for small epsilon in a subinterval a b, which is a proper which is a subset of not proper, it's a subset of x0 and x1. And then what this implies is that the integral of a or a to b f x y prime dx is equal to integral over a epsilon b epsilon of f, which is a function of capital X y epsilon and y dot epsilon dx. Now what you see here is that we define um, capital Y dot epsilon to be equal to the first derivative of capital Y epsilon x with respect to capital X, where the boundary points, which is a epsilon and b epsilon, are themselves the transformed, are the images of the transformation of the boundary points of the original function of original domain, which is a b. And if this relation holds, then the transformation, such transformations are is what we call as the variational symmetry of the functional J. Okay. Now let's briefly look at infinitesimal generators. Now, given the transformations that we just expressed, we just wrote down, which is capital X is equal to theta x y epsilon and capital Y is equal to psi x epsilon. And what we do is we'll expand capital X and capital Y in terms of a Taylor series about epsilon is equal to 0. And if I ask you how are we able to do this, thing is epsilon is a small number, right? And that's the reason we are able to make or we are able to express this quantity x capital X equal to theta x y epsilon in terms of a Taylor series about epsilon is equal to 0. Now so the infinitesimal generators here are, so say let's expand capital X. So capital X is equal to theta xy0 plus epsilon partial theta by partial epsilon at epsilon is equal to 0 plus other terms, plus other higher order terms, which we have collectively um, called as order of epsilon squared terms. And likewise for capital Y. So the infinitesimal generators are xi is equal to partial theta with respect to partial epsilon at epsilon is equal to 0. And eta is equal to partial psi with respect to partial epsilon at epsilon is equal to 0. Now let's rigorously define, state the Noether's theorem. So Noether's theorem is state that suppose our integrand of the function f is variously invariant on the domain x0 x1 under the transformation capital X is equal to theta and capital Y is equal to psi with xi and eta as infinitesimal generators, then eta p minus eta p minus xi h is equal to constant along any extremal where you very well recall the definitions for p and h. So p is partial f with respect to partial y prime, and h is equal to y prime partial f by partial y prime minus f. Or essentially, this capital H is what we call as Hamiltonian. Okay. Now let's talk about how do we find the variational symmetries. So when you take a closer look at Noether's theorem, all that it asks us is to find xi and eta, which are the infinitesimal generators. If we have the infinitesimal generators, then we can very well explain, or we can very well find whether a transformation or whether a functional is subjected, has some variation symmetries, and what are the uh, what are the generators for that symmetry, and that's what we call as the infinitesimal generators. So essentially, our task is to determine the expressions for xi and eta. Okay. Now, how do we find the variational symmetries? Say given j of y is equal to integral of f from x to x naught, is the classic expression that we have discussed several times. Then the transformation capital X is equal to theta and capital Y is equal to psi with the infinitesimal generators xi and eta is a variational symmetry for J if and only if, mind you, there is a very strong statement here. There is a very strong statement, and I should actually put it in a box. If xi into parcel f by parcel x plus eta parcel f by parcel y plus eta prime minus y prime xi prime into parcel f by parcel y prime plus xi prime f is equal to 0, where xi prime is equal to eta prime is equal to eta to y prime, and likewise this is defined as plus partial xi by partial y into y prime. Okay. And so what you see is, although there is just one equation, but however, you'll find that for this, and then what we see is this has to hold for all x is an element of x naught to x1. It has to hold at every point, and for any for and for all y actually. It's for all y, for all functions y. It has to. This expression has to. So what we do is essentially we'll have an expression in terms of the higher order derivatives of y derivatives of y. So and then we have to equate it to 0. So essentially what we do is we'll equate all the powers all the coefficients of y kth derivative of y to 0. And this gives us a set of equations which almost most of the time we'll always have more equations. And essentially using this equation, our goal is to solve for eta and xi, zeta and xi. So which means that most of the time, almost all the time, what you'll see is we'll have multiple equations. So we'll have more equations than the number of variables, so to speak. So this is always going to be, almost always, not always, but most of the time it's going to be an overdetermined system. So in that case, what we do is our goal essentially is to just to find the expressions for xi and eta in terms of uh, up to some integral, up to some constants of integration. So we will have a family of xi. So all we require is to get that family of xi and eta. Okay. And mind you that this is not, we won't be able to obtain xi and eta for any type of functions. They only will be obtained for those functions which allow for, for, variational symmetries. And once you obtain the expressions for xi and eta, then we are able to compute uh, the conservation laws for any system, and that's what Noether's theorem says, right? So this is a conservation law for functionals of whose integrand is this. Okay. Okay. So now let's move on to the next section, next topic, it's in our mm, review process. So this is the second variation. Now I'll ask, why do we need second variation? So before I explain it to you, let's first review the meaning of Euler-Lagrange equation. And since we have been discussing a lot about Euler-Lagrange equations, and fundamentally, Euler-Lagrange equation is when we equate the first variational derivative of, or when we equate the first variational derivative, first variational derivative of the functional to zero, and that's where we get from there we are able to obtain the Euler-Lagrange equations. But what does Euler-Lagrange equation give us? It just gives us the necessary condition for the existence of extremum of a function. Now, and this you'll find that it's analogous to what we do in finite dimensional calculus, wherein we just equate the gradient of the function which we are trying to optimize to zero. But that equating gradient of the function f to be zero doesn't give us. It only gives us stationary point, but it doesn't tell us whether that's local minimum, local maximum, or a saddle. So similar to that, even Euler-Lagrange equation serves the same purpose. Just that in this case, Euler-Lagrange equation happens to be a differential equation, isn't it? So in order to obtain the nature of extremals, we need a sufficient condition or some other condition to be able to uh, check whether the extremal is local minimum, local maximum, or a saddle, so to speak. And that's where the need for second variation comes. Okay. So in finite dimensional case, the necessary condition for extremum of a function f is equal to uh, f which is a function of x1, x2 till xn, isn't it? Now the necessary condition simply states that the gradient of f is equal to 0. And this gives us, upon solving that set of equations, we will have what we call as x is equal to x naught bar, and where x naught bar is a stationary point. You may get several stationary points. So now what we are required to do is to determine the nature of the stationary point, and this is also often the sufficient conditions to determine whether the stationary point is local minimum, local maximum, or a saddle point. For that purpose, we require something called as Hessian matrix. Hessian matrix is defined as h of x naught bar is equal to double derivative of f with respect to xi and xij's. And what you see here is, in this Hessian we determine at x is equal to x naught bar. Now h is definite. In this case, if h is definite, then f has local extremum at x naught bar. And then based on the nature of h, we will be able to, based on the intrinsic nature of h, we will be able to state whether x naught bar happens to be a local minimum or a local maximum. Now h is indefinite, and when h is indefinite, then x naught bar is a saddle point. Okay. Now let's determine the second variation of functionals. Let's review the second variation of functionals. So given a functional j of y is equal to x naught to x1, and same usual function that we have been dealing with, with the boundary and with the boundary condition which are y at x is equal to x naught is equal to y naught, and y at x is equal to 1 is x is equal to x1 is equal to y1. And here what we do is we substitute, or we add a first order perturbation to the extremal y, and this gives us the perturbed quantity is y hat is equal to y plus epsilon zeta, and sorry, epsilon eta, and eta is a smooth function. And again, and as usual, epsilon is a small quantity. The small, I would call it as epsilon is a small number. Okay. Now using Taylor series, we are able to expand j of y hat into about y, and this gives us j of y hat minus j of y is equal to epsilon del j eta and y plus epsilon squared by 2 del squared j eta y plus order of epsilon cubed, where del j eta y is equal to x naught x1 eta del f by del y plus eta prime del f by del y prime into dx, and del squared j of eta y is equal to x naught x1. Then the integrand is eta squared del squared f by del y squared plus 2 eta prime del squared f by del y and del y prime plus eta prime squared del squared f by del y prime squared. Now suppose j has a local extremum at y, then if del squared j is greater or equal to 0, and this for all eta, then this implies that y is a local minimum. And if del squared j is less or equal to 0 for all eta, then y is a local maximum. So with this, we have reviewed, uh, essentially we have reviewed the important concept that we had learned during the week 8 of this course. So we started with the Noether's theorem, discussed about conservation law, and followed up with the need and necessity of the Noether's theorem. Uh, had a brief look at the variational symmetries, the meaning of infinitesimal generators, and then rigorously we gave the statement, or essentially we just gave a statement of the Noether's theorem. Then we talked about how do we find the variational symmetries. Then we moved on to talking about second variation for both finite dimensional case and the case for functions. Now let me start with solving problems. Okay. Just a minute. Okay. So at first we'll be reviewing a few questions on how to solve Euler-Lagrange equations before we move on to solving the problems for this class, which week 8 of this course. At first, let me begin with determine the extremal of the functional of y is it, and this happens to be our functional, and subject to the end conditions y0 is equal to 0 and y1 is equal to 1. Okay, so you know the drill, right? So first our integrand of the function is our integrand of the function. At first we'll find out the Euler-Lagrange equation. And this is defined as d by dx of del f by del y prime minus del f by del y is equal to 0. So this implies that d by dx del f by del y prime is 2y prime and minus del f by del y is 2y plus 2 to the power x is equal to 0. So, and we factor out 2. This gives us y double prime minus y is equal to e to the power x. Right? Now what you see is this is equation. There is an ODE and it's a second order ODE. Second order ODE and it's also non-homogeneous. The thing is, it has one term which doesn't contain y, right? Which is e to the power x. Okay, so let's solve this problem. So you know that for non-homogeneous equation or differential equation, we need to first find the homogeneous solution and then a particular solution and then add them up to get a general solution. And then using end conditions, we will find the constants of integration, right? Okay. Now let's find the homogeneous solution. So for that, we need to solve this problem. Yx double prime minus yx is equal to 0. And you recall very well that the solution of equation of such type is yx of yx of x is equal to c1 e to the power x plus c2 e to the power minus x. And this we can also write as after making algebraic manipulations and we bring in the let's bring in the hyperbolic functions, and then we'll have a sine hyperbolic x plus b cosine hyperbolic x, right? So we have obtained the homogeneous solution. Now let's find the particular solution. Before that, or we know that when we find the particular solution or because essentially in this problem we had taken an unsought for the solution as e to the power lambda into x, right? And then we got two eigenvalues plus 1 and minus 1 or two roots which are plus 1 and minus 1. When we take a look at our original differential equation, which is y double prime minus y square to power x, what we say is this function and one of the homogeneous solution actually match, isn't it? So it simply means that we cannot directly take a solution of the form e to the power x as it is in order to obtain our particular integral. Let me write a particular solution. Now let me just write what we need to solve to obtain a particular solution. We need to solve yp double prime minus yp is equal to e to the power x, right? So what we do is we cannot take a solution of this form. We cannot take yp is equal to say we cannot take this as a model solution, isn't it? This we cannot take this as the model solution because this and this happens to be the same. So what we do is we'll take a solution of an assumed solution of that type as kx to the power x. Fine. Then this implies that yp prime of x is equal to k into to power x plus x to the power x. Likewise, the prime of x is equal to k to the power x plus power x plus x to the power x, and this gives us k to the power x plus x e to the power x, right? Now let's substitute these expressions in this equation here. So then this implies that k 2 to the power x plus x e to the power x minus k x e to the power x is equal to e to the power x, right? So then this gives us and this gives us 2k e to the power x because this term cancels out. 2k to the power x is equal to the power x. And this implies that 2k minus 1 into the power x is equal to 0. Now mind you that for finite x, will e to the power x will never be 0. So that this implies that 2k minus 1 is equal to 0. This implies that k is equal to, right? Okay. So therefore our general solution is y of x is equal to a sine hyperbolic x plus b cosine hyperbolic x plus k is half, right? So we'll have x by 2 to the power x, right? Now let's use our boundary conditions to determine the value of constants a and b. Okay, so from basis, we'll make a copy with it. Okay. Uh, from basis, what we have is y of 0 is equal to 0, isn't it? Y of 0 is equal to 0. So this implies that sine hyperbolic function at x is equal to 0 is 0. So it's what a into 0 plus cosine hyperbolic at x is equal to 0 is 1. So a into 0 into b into 1 plus and x at x, this term, the last term is already 0. So this simply implies that b is equal to 0. Right? Now for the other boundary conditions, y at 1 is equal to 1. So what we do with this is a sine hyperbolic 1 plus e to the power e1 by 2, right? So e to the e by 2 is equal to 0, is equal to 1. So then this we have as a is equal to 1 minus e by 2 sine hyperbolic 1. Okay. So therefore our solution is y of x is equal to 1 minus e by 2 divided by sine hyperbolic 1 into sine hyperbolic x plus, okay, so these are our solution. Now let's move to the next problem. So it says that what is the extremal of the function I is equal to into x2 fine. Okay, as usual, these are integrand of the function f, and the drill is to find Euler-Lagrange equation, which is d by dx partial f by partial y prime is 2x y prime, isn't it? Minus y, right? 2x y prime minus y minus is partial derivative of f with respect to y, so it gives us minus y prime plus 1, isn't it? Minus y prime plus 1. This is equal to 0. Now let's take the first question. So it is 2x y prime. I'll just take 2 out. X y prime minus y prime plus y prime minus 1 is equal to 0, right? So then this gives us, this cancels out, right? So we have x y prime is equal to 1 by 2. So then this implies that xy is equal to xy prime is equal to x by 2 plus some constant c1, right? Now what we do is, let us let's divide throughout by x. So y prime is equal to 1 by 2 plus c1 by x, right? Integrating it again, we have y is equal to x by 2 plus c1 natural log of absolute value of x plus c2. So this is our extreme, isn't it? Okay. Now let's solve the third problem. Third problem is found the extreme of the function 0 to this is again the standard function. So these are f, and when we take a clear look at f, what we see is this function is, this integrand is independent of y prime, sorry, of y. So the solution is we'll use the let's write our Euler equation, which is d by dx of partial f by partial y prime minus partial f by partial y. So this term is 0. So this implies that partial f by partial y prime, so it is 2y prime divided by x cubed. This is equal to some constant c1. And then what we do is, this implies that y prime is equal to c1 by 2 x cubed, right? And we'll integrate with respect to x. So this gives us y is equal to c1 x to the power 4 divided by 4 into 2, which is 8, plus some constant c. So this is our solution. Okay, I think we have had enough warm up. Let's move on to solving the tough questions for this week. Okay, so the first question is, consider the functional j whose integrand is x y prime squared, where our goal is to check whether the transformation capital X is equal to small x plus epsilon to x natural log of x, and capital Y is equal to 1 plus epsilon into y to small y is a variational symmetry for j. Okay, now you very well recall from the definition of variational symmetry, right? Not a function is said to be variationally invariant with respect to some transformation if x naught to x1 capital X y primes, sorry, small x y prime square dx, or I'll just start the definition. So x y prime dx is equal to capital X naught capital X1 of f capital X y epsilon and If this relation holds, then we call as the, which means that even after the transformation, the nature of the equation of the function remains the same. Okay, let's see whether this under the given transformation is will our functional remain invariant or not. So what we have here is capital X given capital X is equal to, I'll just call it as a function of theta of X. And this is given as, I'll just call it theta X, Y, and epsilon, right? And this is equal to X plus epsilon 2X, the natural log of X, and likewise capital Y is equal to psi capital X capital Y epsilon is equal to 1 plus epsilon Y. Now let's take a look at the expression at both the transformations, right? Capital X seems to only depend on small x and epsilon, isn't it? So which means, and what we say is this is nothing but function of just x and epsilon, and even capital Y is, it doesn't contain any term in containing small x. So this also happens to be a function of just y and epsilon. Fine. Now let's find the differentials for both the transformation. So you have dx is equal to, I'll just call it as theta of partial derivative of theta with respect to x into d small y. And likewise, d capital Y is equal to psi small y into y into dy, right? So we have just obtained the differentials. And this, what we see clearly here is that theta small x is equal to 1 plus 2 epsilon, and then x into derivative of ln x with respect to x. So it gives us 1 by x. So x into 1 by x is 1. And this is using the chain rule, and then d by dx by dx is just 1. So we'll have ln of x, right? And psi of y is nothing but partial derivative of psi with respect to y is, oh, sorry, here we are finding the total derivative because psi happens to, let me correct myself, we are finding the partial with respect to y because we also have a term epsilon, right? So this is given by 1 plus epsilon. Okay. Now what we do is let's divide this expression by this expression, right? And you'll see why we are doing it. So d capital Y by d small x is equal to d capital X is equal to psi y dy divided by theta x. And this is nothing but psi y by theta x dy by dx is y prime, isn't it? So then this implies that y dot is equal to, and this can write as epsilon. I just these are equivalent here, the same thing. Y prime. Now, when you take a look at the transformation, capital X is equal to x plus small x plus epsilon 2x and then log natural of x. What you see is it's tough to obtain an inverse function which is express small x in terms of capital X, right? Because of the presence of log. This can be done locally for a small epsilon, but for larger epsilon, we are unable to, we cannot, or in the sense that we are unable to obtain a true inverse, so to speak, that small x in terms of capital X, right? So when we'll be finding the variational symmetry, we will be going the other way. We'll start with here and go backwards. This is just because of that it's tough to express small x in terms of capital X, right? Okay, so what I do is let me start with the x, capital X naught, capital X1, f, capital X. I'll just write the expression here, and the integrand will be y dot squared t of x, right? So this I can write as x naught, x1, and x as x is nothing but theta. I'll just write theta here, and y dot square is psi y by theta x into squared and even y prime squared. And then dx I can write as theta x dx. Now after doing this, you'll see that now our integral is in terms of the, now we are integrating with respect to small x, so we'll have to change the limit. So this becomes small x naught and this becomes, okay. So then this implies that x naught, x1, and what you say is theta into psi y squared divided by and theta x squared, and then you have theta x here as well here. So this cancels out just to give us theta x and y prime squared into dx. Okay, now let's substitute the expressions. X naught, x1. Now here theta is this we can also write as taking x as a common factor. We'll have 1 plus 2 epsilon ln of x. And I'll just write x y prime squared 1 plus 2 epsilon ln of x, and psi y is 1 plus epsilon, right? It is 1 plus epsilon. So this is 1 plus epsilon whole squared divided by theta x, which is given as 1 plus 2 epsilon 1 plus log natural of x, and then dx. Now when you take a look at this expression here, what you see is this term is not equal to 1. There is no cancellation going on. So it simply means that this entire expression is not equal to x naught, x1 is not equal to. So it simply means that the given transformation is not. I'll just move this here. I'll just remove this. Okay, is not a variational. Is not. Let me emphasize. Is not a variational symmetry. Okay. Now let's move to the next question. In this question, what we are required to do is, let me do another problem. Let me just save this upwards. Let's solve a similar problem first. Okay. So here we have a functional j containing x y prime squared. We have the same function. So we are asked to show that the transformation capital Y is equal to y and capital X is equal to 1 plus epsilon into x is a variational symmetry, and find the corresponding conservation law. Fine. So at first, let's determine the Let's determine our let's have on it x, capital X is equal to 1 plus epsilon into x, and we can, let's find the inverse or and this we can express in terms of x is equal to capital X by 1 plus epsilon, right? And the differential is dx is equal to d capital X by 1 plus epsilon. Likewise, capital Y is equal to y, so this implies that small y is equal to capital Y, and this gives us dy is equal to d capital Y. Right? Nowadays, let's proceed. In the previous question, we went from this to this, right? In this case, let's move from left to right, right? So let's start with x naught and x1. We'll have x y prime squared dx. Let's substitute the expression for x, which is capital X divided by 1 plus epsilon. And using this, we'll have dy by dx is equal to 1 plus epsilon d capital X, and this we can call as y prime is equal to 1 plus epsilon into capital Y dot. There's a subscript is epsilon, so then this we have as 1 plus epsilon squared to y dot epsilon squared into dx is d capital X by 1 plus epsilon. And since we have transformed our both x and y, so the limits of integration will be capital X naught to capital X1. So this gives us x naught x1. And one epsilon cancels out, so we have capital X y dot epsilon squared dx, right? I think this was better. Now, when you take a look at the expression clearly, what you see is the expressions have the same form, isn't it? Even after uh, transforming the quantities as small x and small y under using a family of using a transformation which is parameterized by epsilon. So then this simply means that the given transformation is a variational symmetry for the functional j. Fine. Now, since the given under the given transformation, our functional remains variously invariant, so we can invoke our Noether's theorem. In that case, our conservation law from it comes from Noether's. It follows from Noether's theorem. It states that eta p minus h xi is equal to constant. Now, you very well recall that eta and xi are infinitesimal. What are these infinitesimal transformations, right? I hope you recall infinitesimal generators. Okay. Okay. So, and this is defined as here eta is defined as okay. First, xi is defined as del x by del epsilon, partial epsilon with eta power epsilon is equal to 0, and this gives us x, right? So partial x with respect to partial epsilon is x into x epsilon, right? So it's just x, and then eta is partial y with respect to partial epsilon is equal to, and you see that capital Y is identity equal to small y, so there is no transformation going on. It's an identity transformation. It's a trivial transformation, right? This is nothing but 0. And p is equal to partial by partial y prime, and this is nothing but this is our f, right? So this gives us 2xy prime, and h is equal to y prime p minus f. So y prime into 2xy prime minus xy prime square, and this gives us just xy prime squared. Fine. So our conservation law is 0 into 2xy prime minus xy prime squared into x equal to constant. And then this implies that x square y prime squared is equal to constant. And then this we can, okay, we can stop here also. So essentially there is our conservation law. Right. And if you ask fine, how do you verify that this is the conservation law? Mind you that this functional, the integral of this functional doesn't contain, will think, no, let me not go into that, sorry. So this is our constant, this is our conservation law here. Okay. Now the next question is determine the variational symmetry for J of y, and this is equal to just a minute, let's check. Okay. Okay. So we need to determine the variational symmetry for J of y of this functional here, and whose integral is this. Integrand is this. So determining the variational symmetry is essentially determining. So the solution goes as we need to determine what do we need to determine? Infinitesimal generators, right? Which are xi and eta. Fine. Okay. Now let's go back to the equation that we had to solve to obtain this. So we need to solve this equation, right? We'll just copy from here. Paste here as well for our reference. And we'll copy this. So this is what we require. And paste this here. Fine. Okay. So first of all, I'll just keep it here. Okay, so what do we require first? First we require partial f with respect to partial x, right? Now partial f over partial x is 2xy prime squared. Partial f over partial y is 4y cubed, and partial with respect to partial y prime is 2x squared y prime. Fine. And we already know that the epsilon prime is, I will write L in terms of subscript plus y prime, and likewise. Okay, now let's substitute all these expressions in this equation here. So then this implies that xi into 2xy prime squared plus eta into 4y cubed plus eta x plus eta y prime minus y prime, and I'll expand it, minus y prime squared subscript 1, and then this multiplies with 2x squared y prime, right? Single dip, fine. And then we have plus the new line. I'll just call it as plus y prime into equal to 0. Okay. Okay. Now what we do is let's collect all the terms. Let's first expand all the terms. We have 2x y prime squared xi plus 4y cubed eta plus 2x squared eta x into, even this I should have y prime plus 2x squared eta y into prime squared minus 2x squared xi x y prime squared minus 2x squared xi y prime cubed, isn't it? And plus x squared xi x and squared plus, and then what we'll do is plus y to the power 4 plus x squared xi y prime cube plus y4 y into 0. Right. Now what we do is let's collate all the terms. I think this is done on the next slide. Mm. Now then this implies that we'll first collect all the terms with y prime cubed, because I think that's the highest order derivative, right? I mean, y prime raised to the highest degree, so it's y prime cubed. Let's start with that. So at first what we have is minus 2x squared epsilon y. So these terms is gone away, right? And plus x squared this term. So I think there are no other terms with y prime cubed, right? Okay. Now let's you know, better to write it in the at front, right? I'm sorry. Okay. Now for y prime squared. So the first term is 2x, so this goes out. And then we have plus 2x squared eta y comes out, and plus xi of x. This is not right, so we have. I hope I'm not making a mistake. Mm, so let's just review. Minus, right? It's minus here, minus. Okay, so there is one more term here with squared. This is also squared. Okay, so we'll have one more term. First, second, this as well. So with this, we are done with y prime squared terms. Now let's come to y prime containing terms. So with this, we have the first one, which is x squared eta of index. This goes, and the other one is y to the power 4 xi y prime. Oh, sorry, we have already accounted for this. This goes. Now let's write down the remaining terms. So we have plus this goes. This goes. Fine. So with this, we have covered all the terms. Doing this. Fine. Now what we do is we will equate the coefficients of y prime cubed squared y prime to 0. And then also sort down the final term. I mean, the remaining terms that's already equal to 0, right? So first y prime cubed. So with this, we have 2 minus 2x squared y plus x squared. And what you clearly say is it's minus 2x squared xi y and plus x squared xi. So essentially, it is just minus x squared xi y is equal to 0. Y prime squared, we have 2x xi plus 2x squared eta y, right? And then what you see is plus x squared xi x minus 2x squared xi x. So essentially it is minus x squared. And for y prime we have x squared eta of x plus y to the power 4 xi y is equal to 0. And the remaining terms. Since this equation was already equal to 0, so we are left with 4y cubed eta plus y to the power 4 and x is equal to 0. Fine. Okay. Now let's start solving this set of equations for xi and eta. So our goal was to obtain the expressions for xi and eta. Okay. Define. On the first equation, what we see here is this equation says that minus x squared xi y is equal to 0. And you know that this has to hold for all x. So which means that x is not 0 everywhere. So this simply means that xi y is equal to 0, isn't it? And if a partial derivative of a function y is 0 with respect to y is 0, so this simply means that function y doesn't contain any term with function xi doesn't contain any term with y. So it simply means that xi is a function of x. Fine. So this was the first conclusion. Now let's take at this equation here, this, and here you say that xi y, there is a term containing xi y, but we have already determined that xi y, partial derivative of xi with respect to y is 0. So this means that x squared x is equal to 0. And similar to the argument that we had used in the previous solving for the while solving the previous equation, which is x squared xi y is equal to 0. Here, even in this case, what you see is that for arbitrary x, when this expression is 0, this simply means that eta x has to be 0. And the conclusion is that eta is a function of y only. Y only. Fine. Okay. Now let's go to this equation here, and let's do some rearrangement. What we do is let's divide throughout by y4, so that we have y4 eta plus, and then this implies that 4 by y eta plus xi x is equal I can just write is equal to um, I can write this equation as minus is equal to, now what you see here is this is purely a function of x and this is purely a function of y, right? This follows from eta is being a function of y. So that for both the equations to hold, for this equation to hold, you must have both the quantities to be equal to some constant c1, right? So then this implies that eta is equal to minus c1 by 4y and xi x is equal to c1. Now, upon integrating it, we'll have xi is equal to c1 plus c2. So we have the constant c1 and c2, which are need to be determined, fine, to have a. Okay, now let's take the help of we have not yet touched this equation, right? This equation we have not yet touched. Now let's do that now. So for this, what we have is 2 into x and xi is c1 x plus c2 and plus 2x squared, and xi y, sorry, eta y is minus 1 by minus c1 by 4. So minus 3 minus c1 by 4 minus x squared into c1, right? And this gives that. I think I'll just take this down here, get to for us to have more room. I'll just call that we are solving this equation here. Solving this equation here. And this was supposed to be 0. So then this implies that 2c1x squared plus 2c2x minus c1 by 2x squared minus x squared c1 is equal to 0. And this implies that we have this term, and these three terms have the same we can have the same term factor within it, which is x squared. So we can after doing the algebraic operations, what we are left with is this gives us c1 by 2x squared plus 2c2x is equal to 0. Now for this relation to hold for all x, this is only true if c1 is equal to 0 and c2 is equal to 0. If both c1 and c2 are 0, then this implies that eta is equal to minus 0 into y, so 0, and even xi is also c1x is equal to 0. So which means we have trivial expression for xi and eta, which is not non-zero, right? So which means that J has no variational symmetry. This is our conclusion, because our infinitesimal generators are trivial, has no variational symmetry. Has no variational symmetry. Okay. Now let's solve the one more problem of this type. Okay. Now in this problem, what we are required to do is there's the Emden Fowler equation of astrophysics is y double prime plus 2 by x y prime plus y to the power 5 is equal to 0. Okay. And this equation arises out of arises as the Euler-Lagrange equation for the function, which is given here. And the question asks us to find the infinitesimal generators that lead to a variational symmetry for this function and establish the conservation law. Okay. So we have many things going on here. First, we need to determine the infinitesimal generators, and then establish the conservation law for the problem. Right? Okay. Okay. Now let's start with. Let's take. I'll copy this here as well. Okay. And paste it here. Paste. It was. Okay. So the integrand is, you know very well, these are integrand. This is f, right? So let's start with so partial f, so partial x is x into y plus 3, right? Partial, I'll call it partial f by partial y is x squared by 2 into minus 6 by 3 y to the power 5, and this evaluates to minus x square y to the power 5. Okay, and partial f by partial y prime is x squared by 2 into 2y prime, and this gives us x squared y prime. Okay, I think let's take another slide. Okay, first of all, xi partial f by partial x is I'll just call x into y prime squared minus 1 by 6 by 3 and plus eta minus x squared y to the power 4 y to the power 5 and x plus eta y. So I prime eta y xi y and this multiplied with x square y prime, and finally we have plus y prime so y2 and this evaluates to 0. Okay, now let's expand. Also let's so the first one is x xi into y prime squared, and the second is x y to the power 6 by 3 into xi, and this is minus x square y to the power 4 eta, and for this we have x square eta x y prime plus x square eta y prime squared minus x square xi x to y prime squared minus xi y prime cubed plus what we have here is x square xi x by 2 to y prime squared, and then minus x squared y to the power 6 xi x by 6, isn't it? Right? Plus x squared xi y by 2 into y prime cubed minus x square to the power 6 divided by 6 and into xi y, and this multiplied y prime square by 6. And okay, now let's correct all the terms. Y prime cubed is, which terms have this. First is minus x square xi y, right? This gone. And the second is plus x square xi y by 2. This gone, right? So now with y prime squared, first is xi is gone, and the second is plus x square eta y, so this gone. Third is minus x square eta x, this gone, and the fourth is x by 2, this gone. And how about now? Let's know for the y prime term. For that we have x squared eta x, right? So this gone, and we have one more which is x squared over 6 by 6 eta y. And how many terms we have? Now the rest are what? By 3 xi minus x squared eta minus x squared. So this gone, this gone, this also fine. Okay. Now we need to equate maths coefficients, right? Or maths coefficients to 0. Y prime squared y prime to 0. I think we should do this in the next slide. Okay. So first of all, let's start with y prime cubed. When we take a look at this, clearly we have minus x squared xi y plus x squared by 2 xi y. So effectively we have minus x squared xi y by 2 is equal to 0, right? Yeah. And the second is y prime squared. This also need to equate to 0. So for this we have x xi plus x square eta y, right? X xi plus x square eta y. And then in the last, we see the last two terms can be added up to have minus x squared by 2 xi x. Okay, minus x squared xi by 2, fine. Yeah. Now y prime. So here we have x squared eta x minus x square y6 y to the power 6 by 6 xi y. X square by 6. Isn't this square y 6 by 6? Okay. Now the remaining terms, what I'll just copy from here. Come on. Fine. Okay. What we do is, since all the terms contain minus, and this actually equates to 0. So this is actually equal to 0. So all that we require, we can just multiply both sides by -1. So we'll have plus plus. Fine. I think I've dropped one the first x. Sorry. So this is x y to the power 6 and x. Yeah. This is the remaining actually. Okay, now let's start solving this equation. This set of equations. So from the first case, since this equation has to hold for all cases of x, so this simply means that xy is equal to 0. And this means that xy is a function of x only. And likewise, we can use xy is equal to 0 in this the third equation. And this gives us x square eta x is equal to 0. So then this means that eta x is equal to 0, or eta is a function of y only. Fine. Okay, so far so good. Now what we'll do is from the final equation we just divide throughout by x to the power 1 by x squared y to the power 6. Shifted sideways. So we'll do this operation. And this gives us xi by 3x plus eta by y plus xi x by 6 equal to 0. Isn't it? We can rearrange this to have minus eta by y is equal to 3x plus xi x by 6. And since xi is a pure function of x and eta is a pure function of y, for this to become both the equation to hold, we must have both the terms being equal to some constant c. So this means that eta is equal to minus c1y. And for the second, we'll just multiply throughout by 6. And this gives us plus 2 xi by x is equal to 6c1. Right? Okay. Now let's put whatever we know in this expression here. So we have x into xi. Before that, let me do something. Okay, leave it for now. What we do is let's put whatever we know so far here. Xi plus x square eta y is nothing but minus c1 minus x squared by 2 xi of x is equal to 0. Let's divide throughout by let's first divide throughout by x squared. So we'll have just 1 by x squared throughout. And then this gives us xi by x minus c1 and minus xi x by 2 is equal to 0. And then this we can write this as and multiply by 2 and then make some manipulations. So we have minus plus 2 xi is equal to c1. Fine. Is equal to 2c1. Okay. Now we need to solve these two equations. this and this. Adding gives us 4 xi by x is equal to 8c1. And this gives us xi is equal to 2c1 into x. We already have, and this we have got. If you want to verify whether this equation really holds, so let's just check. Minus xi is minus 2c1 plus 2 xi is sure c1x by x is equal to 2c1. Fine, so this holds. Okay. So essentially we have infinitesimal generators there. What are this? So we have xi is equal to 2c1x and eta is equal to minus c1y. Okay. So let's form the conservation law. Okay. Okay. From our Noether's theorem, what we have learned is the conservation law is given as eta p minus xi into h is equal to. Now p is equal to del f by del y prime, right? And what we have p del f by del y prime, we already know is x squared y prime, extension y prime, and h is equal to y prime p minus f. So y prime into x squared y prime minus of x squared by 2 y prime squared minus 10 to the power 6 by 3. Okay. So this gives us x squared y prime squared minus x squared y prime squared by 2 plus x power per 6 by 6, right? Okay. And this effectively is x squared y prime squared by 2 x by 6. Okay. So the conservation law is minus c1 into y into x squared y prime minus 2c1 into x and into x squared y prime squared by 2 plus x squared y to the power 6 by 6. constant. You can just factor out minus, multiply through, divide by minus c1. So then this gives us x squared to y into y prime plus 2 into x and y prime squared by 2 plus y to the power 6 by x. So these are conservation law. Let me highlight this. So these are conservation law. Okay. Let's solve one more question in the topic of second variation. So here we have jy the functional is and then the function, and then suppose that j has a local mixed extremum at y. Use Legendre condition to determine the nature of the extremum. Okay. So we'll use our Legendre condition. I'm sorry I did not write it here. Okay, but anyway, I'll just state what Legendre condition is. So the Legendre conditions states that f y prime or ideally, I mean, I should split is del square f by del y prime squared. This should be equal to 0, equal or greater than 0 for y to be for local maximum, local minimum at extremum y. Okay. So this is our Legendre condition. Okay. So let's first find del f by del y prime. And this is given as y squared first, and then minus 2 into y prime to the power minus 3, isn't it? So this gives us minus 2 into 1 plus y squared divided by y prime cubed, isn't it? Now, again, what we'll do is del square f by del y prime squared is again, we'll have minus 2 into 1 plus y squared, and this gives us minus 3 into y prime to the power minus 4. So we will have minus 3 into minus 2 is 6, 1 plus y squared divided by 4. Now let's evaluate. What we see is 1 plus y squared is always going to be greater or equal to 1. It's equal to 1 only when y is 0 throughout. Fine. And if similarly even derivative, I mean, y, the denominator is going to be greater or equal to 0, right? And this assuming that y prime is never 0 anywhere, this is strictly, I mean, assuming that y prime is never 0 at any point. So this is always greater than 0. So effectively, this term is always greater than 0. So then this means that jy has a local minimum at the extremum y. Okay, one last question. One more question. I have not yet written the question. So geodesics on a sphere of radius r greater than 0 correspond to the extremals of the functional j phi is theta naught theta 1 plus sine square theta phi prime squared to where phi is the polar angle and theta is the azimuthal angle, and phi prime is equal to d pi by d theta. So we have to show that j satisfies the Legendre condition. Okay. So we'll first write down our integral of the function, which is f, and this happens to be theta, phi, and phi prime. And this is given by 1 plus sine squared theta and phi prime squared, isn't it? Okay. Now let's find the del f by del phi prime. And this is given by 1 by 2 into, I'll just call it 1 plus sine squared theta phi prime squared into minus 2 into 2 into phi prime, right, using the chain rule. So we'll have phi prime divided by, phi prime into sine squared theta phi prime, isn't it? So this gives us sine squared theta phi into phi prime divided by 1 plus sine squared theta phi prime squared. Taking second derivative of phi with respect to f with respect to phi prime. So we'll have this is equal to, again, I will use our find the derivative of the ratio of functions, right? So we'll have sine square theta into so this goes away, so we'll have root over 1 plus sine square theta into phi prime squared, isn't it? Minus into phi prime, and then essentially the same. So this gives us sine to the power sine square And this is 1 plus sin square theta 5 prime squared, right? Okay. And what we'll do with this is I could have factored out sin square, factor out sin square theta, and 1 plus sin square theta. And this is as root over 1 plus 5 prime square, and this is 1 plus sin square theta into 5 prime square minus sin square theta to 5 prime squared, isn't it? This cancels out, isn't it? And so we are left with sin square theta by 1 plus sin square theta into 5 prime squared to the power 3 that. Now what this is, the numerator is always going to be, this is always going to be greater or equal to 0. Denominator is always going to be greater than 1, greater or equal to 1. Effectively, this term is effectively given by, so then this implies that f of 5 prime is greater or equal to 0. So it means our Legendre condition is satisfied uh, for minimum to exist at extremal phi, which is a function of theta. So it means Legendre is satisfied. LC, I'll just call it as LC is satisfied at all points. Okay. Okay. So with this, we have ended whatever I had to discuss in this session. And do you have any problems? Any questions? Okay, it seems that there are no questions, so let's wind up today's session. I will be discussing reviewing the week 9 of the course in the tutorial in the upcoming tutorial on 28th March. So wherein we'll be talking about furthermore on the second variation. Okay, so let me stop sharing a screen. Let me first stop recording and